So, unlike most math classes, today we get to start off with what do I use this for? So, let's suppose that we had a population. It's a bacteria in a really big environment. Environment. Whatever. You're growing bacteria in Minecraft, right? So they can keep growing in every direction forever without running out of resources. Please note, this is one of the things we're going to talk about a lot in here. This is a model, right? This is not the way bacteria actually work. It is a guess as to how bacteria might work, right? It's a thought experiment about bacteria, not actually how bacteria work. Does that make sense?
It's not a general equation for it.
This is something that will approximate the behavior of bacteria for a while. Does that make sense? Like, this might be a good guess. This would be a really good guess if you introduce 10 of a new strain of bacteria into the pond for the first 7 or 8 days, right? But after those 10 bacteria filled the pond, then you're running into problems that weren't part of this model, right? So my first guess is that basically bacteria grow in such a way that the number of new bacteria there are is basically proportional to the number of bacteria that there were a second ago. You guys see that? So that, and this is the model part, right? I'm writing P prime as Kp. And I'm just saying the derivative is some constant times the population itself. You guys all good with this? Another way I could write this is I could write dp dx is Kp. You guys all with me on this? Okay, and now I'm going to show you a trick called separation of variables. And I want you to get on board with the idea that it's a trick. And just trust me for a second. I'm going to write over here. What follows is a trick. This is not math. It looks like math, but it's not math. Okay? So what you do is you get all the x's to one side and all the p's to the other. And you do this in the dumbest possible way, which is there is an x down here. So you multiply both sides of this equation by dx. None of you are fundamentally uncomfortable with this.
Divide by p.
Yeah, and divide by p. So, and multiply by 1 over p. So you get 1 over p dp is k dx. Yeah, and then you just slap one of those squiggly things on here. So you just multiply both sides by the squiggly thing. So you get the squiggle of 1 over p dp is the squiggle of k dx. No. I'm doing indefinite integration here.
So you're going to have a constant.
So I'm going to get a constant.
Which is, now here's the thing, you would pick to only include it on one side, right, instead of both? Because technically when you integrate both sides, if it's indefinite, you'd have a constant on both sides.
Sure.
Can you fold it into a constant only being on one side?
Yes.
Okay.
I'll show you.
Okay.
So let's integrate 1 over p dp.
Which is ln the absolute value of p.
So you get the natural log of the absolute value of p plus some constant that came from the p side. then on the other side we got the antiderivative of k with respect to x. Kx. Oops. Plus some constant that came from the x side. Okay. Then subtract Cp from both sides. Get the log of the absolute value of p is equal to kx plus cx minus cp.
Couldn't you just add one big C, or do you have to?
Yeah, cx minus cp is just some constant I don't know, right? So I'm going to collapse that. And I'm going back to black here because my claim is that this at this point, so I did a trick, right, which I highlighted it in green. And now at this point, it's not a trick anymore. This is what you would actually get. And I'll tell you in a sec where that came from. So here I got natural log absolute value of p is kx plus a constant. You guys all with me on that? Okay, next.
Multiply each side by e.
Close.
Exponentiate both sides.
Exponentiate both sides, right?
That's
So,
cool.
Yeah, I didn't know that was
Yeah.
the term for it.
so multiplying both
Just
sides
go
by
it,
e,
I
right?
go E it, just E it, everything.
Yeah, you could do e it, right? So if you multiply e times the natural log, right,
That's natural log of p to the e.
is just, yeah, the natural log of p raised to the e power according to a log rule. To get them to undo each other, you need to actually apply the function exponentiation to both sides, right? Don't say that word to the Algebra 2 students, though. It's scary. Just slap a e underneath both sides, right?
You get less appointments that way. It's fine.
So do e to the stuff to both sides, right? And you get the absolute value of p, right, is e raised to the kx plus a constant c.
So we can separate that.
And then you can up your algebra game a little bit, or show me your algebra game a little bit.
Plus or
It can never be
minus,
negative,
yeah.
first of all, unless c is negative.
Well, if it's
Well, that doesn't
a,
make
it's a
any
population rate, isn't it?
Yeah.
The growth rate can be negative.
Ooh, but c is the initial population, so that can be negative.
That's
Okay, wait, c is not the initial population though.
true. Isn't it?
Okay.
So, exponent rule here. So if you have e raised to the kx plus c, you can break that into e raised to the kx. Okay. So I have absolute value of p is e raised to the kx times e to the c.
Yes.
C.
Yeah, and then e to the c is some other constant, right? So I'm going to relabel that thing a. So I'm going to relabel this as a e to the kx.
E to the c is the initial population.
Yeah, e to the c is the initial population. And then, please note, a was supposed to be either positive or negative. Why? Because there's an absolute value over here. So if you want to get the absolute value off, right, you just go like this. And you do plus or minus.
Do you need a plus or minus
But
though,
it
because
can't
it's
be
a
negative.
constant, like,
Totes. It's a constant pitching. Is all good with that? So maybe let me write that stuff down carefully. So I apply plus minus to both sides, get p is plus or minus a e to the kx. But a is an arbitrary constant, so it could be either positive or negative. So relabel to here.
That's cool.
It's all good with this? So there's my exponential growth that I was expecting to see. And if you guys are fans of the PERT model, right? What's A?
A number?
Maybe not.
Yeah, that's the initial population, right? Really, that's me thinking, hey, if you plug x as 0 in here, you get A out. So, in full disclosure here, I have p as a function of x, right? The population as a function of time is A, which is the initial population, times e to the growth rate times x. It's all kind of with me on that? And then the cool thing about differential equations is you can always just check the answer.
Yeah, just differentiate.
Yeah, so you did a bunch of work to get to here, right? Checking the answer is usually pretty easy. You just need to go back to the original equation, so you go find your original equation that said P prime is Kp, right? So here's what P is supposed to be. So I'm wondering, right? Is P prime going to be K times A e to the Kx? Well, I got to take P prime, right? So differentiating, I got A, and then I need a derivative of e to the Kx, so you get e to the Kx times K.
Oh my god.
Check. Cool. Guess all good with that? So, in other words, if we had some bacteria in an infinite environment, right, where they obeyed the rule, P prime is proportional to the population, right, or the population growth rate is proportional to the population, then it has to follow this exponential law. Cool. Questions, things? So what do you use this for? Anytime you can make a statement with physics about the rate in terms of the thing, then you're going to end up doing a differential equation. And the really neat thing is oftentimes you can just write the rate, like you can just write the differential equation down pretty easily. And a lot of the things you know in physics as laws, they really lend themselves to writing a differential equation. So the things right off the bat are gravitation. Pretty chill, actually. Hooke's law.
Also chill.
You guys remember Hooke's law?
Linear, whatever, differential.
Hooke's law is a spring, right? So it says that the acceleration or the force of a spring is proportional to the distance displaced from center, right? So later we'll write this down. It's in the second order chapter, so it'll take us a little bit to get there. But you just write it down, and then you solve it, and you're like, oh hey, yep, I see the sines and cosines. Cool, check. It's really, really rad. So anytime you can make some statement in physics about a rate and a thing, you can often just write the differential equation and solve it. And then you can check your differential equation against reality, right? Which is really where most of those laws came from. Cool? All right.